Today's lesson is about a really pretty crazy concept, which is actually pretty easy to work with. It's called an infinite geometric series. In your videos for today's lesson, you learned that a geometric series is a series whose terms are products of the previous term, meaning you just keep multiplying by the same number. We call that the common ratio to get to the next term, like 2, 4, 8, 16. That's a geometric series. An infinite geometric series is if you were to keep doing that forever and add up the numbers that you get, like 9 plus 3. So you can see what I did there was I multiplied by 1/3 plus 1/3 plus 1/9 plus 1/27. If I keep adding like this forever and ever and ever and ever and ever, what will my sum end up being? Well, you notice that every time I multiply by 1/3, my next term gets smaller and smaller and smaller than the one before it, because I'm multiplying by a number less than 1. Whenever that's the case, whenever you are simply multiplying by a number less than 1, or a number whose absolute value is less than -1. So this works for if you're multiplying by like a -1/3 too. This series converges. This is a big fancy word. You get to BC Calc in a couple of years, you'll learn a lot about the word converges. All it means is it gets closer and closer and closer to a specific number. It doesn't get infinitely bigger. For example, the number we discussed a couple of weeks ago, E, converges on. It gets closer and closer and closer to 2.71828, dot, 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 dot. Well, if the geometric series that goes on forever and ever and ever and ever still converges on a single sum, we need a way to find that sum. Luckily, it is actually a pretty easy formula. It is that the infinite sum is equal to a1 over 1 minus r. The first term divided by 1 minus r. Now, remember that r is a fraction. So 1 minus r is still going to be a number less than 1, as long as it's positive. If r is negative, then 1 minus r is going to be a number a little bit bigger than 1. But we're taking a1 and dividing it by some fraction, which means we're going to get a number that's bigger than a1. That'll be our infinite sum. So here's an example. Joe puts $10 into a piggy bank. The next day he puts in half as much, so that would be $5. And then the next day he puts in half as much of that. And if Joe keeps doing this, and if Joe and his descendants keep doing this tradition forever, always putting in half as much money as the day before. Now, pretty soon we're going to get to less than a penny, but you can use his, use his computer, put it into his bank account online. I don't know. There's a way to do it. So he will be putting in less than a penny, but he can still put in half as much every day forever. So $1.25. The next day will be half of $1.25 is 62.5 cents. And keep going. Now, his descendants will do this until the end of time. The question is, how much money will there be at the end of time after they're done doing this an infinite number of days? Well, we can use the formula. Because the r is less than 1, in this case r is 1/2, because r is less than 1, we can find the infinite sum using a1 over 1 minus r. So our a1, our first term, a sub 1, is 10. And so that means the infinite sum is equal to 10 divided by 1 minus 1/2. Well, 1 minus a half is a half, and 10 divided by halves is 20. So at the end of time, Joe and his descendants will have saved $20 in their piggy bank. Which is crazy to think about. How much of that is just in like the first 3 terms? He's already up at $17.50. And, well, he's most of the way there. Even between then and the end of time, he's only going to get another $2.50. It's a pretty crazy thought. Just a quick note that if we were to write that using sigma notation, we would use the formula, what he's starting with, and using the formula for a sub n for a geometric series sequence that you saw in your videos for today. Each term in the series could be found by taking the first term and multiplying it by the common ratio n times, or not n times, but n minus 1 times. Starting with the first term and going on until forever. So you can have a sigma notation with an infinity on there. It's a little bit better if you have a legible infinity, so we'll try that again. So in this case, this would be the sum of 10 times 1/2 to the n minus 1, starting from n equals 1, going to infinity, and we learned that that is equal to 20. Okay. We'll see a couple more examples here. Let's say he would have put the same $10 in the piggy bank, but realized, if I save less money every day, that's not going to get me very far. Why don't I try and save more money every day? So this time, he's going to put in twice as much. He'll start with $10 the first day, and $20 the second day, and $40 the third day. And so this time, the R isn't 1/2, the R is equal to 2. So if Joe and his descendants continue this tradition forever, how much money will be in the piggy bank at the end of time? Well, that I can't answer. Because since R is bigger than 1, the series does not converge, is the fancy language we use for this. All it means is this series gets infinitely bigger. There's no way to say what this equals at the end of time, because it always just keeps getting bigger and bigger and bigger and bigger without bound. We'll do one more example of this here. A basketball falls from a height of 12 feet, and each bounce is 1/3 the height of the previous bounce's height. So the first bounce is 12, the second bounce is 4, the next bounce is 4/3 of a foot, and then 4/9 of a foot. Keeps getting smaller and smaller. So the question is, according to this model, which admittedly ignores some rules of physics, but pays attention to most of the important ones, when will the ball stop bouncing? Well, it'll keep having a smaller and smaller and smaller bounce, but it'll never actually stop. But, and this is where the craziness of infinite series comes in, the total accumulated height, if we take the 12 feet it fell on the first fall, plus the 4 feet from the second, plus the 4/3 of a foot from the third, and the 4/9 of a foot, and if we add up all of these forever, how much will all of that add up to? That will add up to a specific number. It's this crazy idea that you could add forever and not get infinitely big. The first bounce was 12 feet, and each bounce after that is 1/3 of the bounce before it, and so the infinite sum would be 12 over 1 minus 1/3, or 12 over 2/3, which is 3/2 of 12, or 18 feet. It'll bounce forever, and will bounce a total of 18